everyone. Let's talk about French multimedia. Alive 2007 is a Grammy Award-winning live album from Daft Punk. The performance and tour it captured was technologically and artistically groundbreaking. They pushed the limits of digital audio workstations to remix and mash up their entire catalog live, on the fly, with spectacular visuals. You can see echoes of their approach all across modern live EDM. An element I love about this style is the sonic ambiguity of the transitions. It's like the musical equivalent of a good, well-constructed joke. For instance, to transition between tracks 4 and 5, the band layers on elements from 2 of their most popular songs, each landing one at a time, along with some new beats until the final mashup erupts into the lyrics. You can hear in the crowd how electrifying it is to be held in sonic suspense, the tension between the familiar riffs and the novel composition. And just like a good joke, timing matters. If you hear a big gap in the playback between the tracks, it reveals the structure and breaks the ambiguity. It explains the joke. The idea of a gapless album isn't limited to live recordings. Studio records have been doing this for over 50 years. And to prove I'm not just an old man talking about a dying medium, I will mention how satisfying it is when a short-form video syncs perfectly back with itself on a loop that, at its best, recontextualizes the whole experience of watching. And for that same reason, I will refrain from making this a talk about the arcana of the CDDA standard. If you're interested in that stuff, you can read about pre-gap shenanigans on your own time. So instead, I'll liken these experiences to a long concert video. The underlying unit of experience here is the whole performance, but we can index into it with chapter markers to find specific songs. So it's natural that this thing plays continuously because it's all one video. So if that's a solved problem, why am I giving a talk about it? Money. In this case, the money that we owe to writers and performers of the songs. Basically, all of the music world does rights accounting by the track. So even if the artist designed the album to be listened to continuously, it gets delivered to platforms as a series of individual tracks. Metadata can then join tracks into an album, but it's risky from a policy point of view to try and merge these before processing. So you have to make them play seamlessly at playback time. And that's harder than you might think. To explain why we have to do a very hand-wavy intro into the basics of audio compression, we will sacrifice precision for brevity. For instance, we will define sound as a change in pressure over time without getting into the many details about how that's actually not quite right. But we capture and play sound with transducers. This is a dynamic microphone, which uses that pressure to push on a little piece of Kevlar, which then shakes a magnet back and forth in time with pressure waves. And then there's a wire that sort of measures that shaking, and that gives us a pretty direct way to see that change in pressure over time. We call this an analog signal, because the signal behaves analogously to the physical medium. And yes, we've shown a digitally quantized version of that analog signal here, but I urge you not to get hung up on that detail. As Monty memorably demonstrated, there are basically no practical differences for listening purposes on any decent hardware. I promise, you did not notice when your favorite concert hall swapped out a digital snake with cleaner preamps and lower distortion. Analog is useful for a few reasons. Because it's so close to the mechanical view of sound, it's really direct to translate back and forth. And that also means certain operators work in a very physically similar way. Adding a voice to a choir in a physical room is essentially the same as adding the electrical signals right together. And critically, these operators work continuously with basically no delay. That's really important for live music production. We're already fighting the speed of sound in a large venue. But your brain does not work in the analog domain. Sure, the eardrum works like a microphone as an AC-coupled transducer, but this magical squiggly bit, the cochlea, transforms the audio signal into the frequency domain, then differentiates the changes and encodes that for transmission to the brain. So instead of an analog signal, what your brain gets is a time-varying view into the frequency spectrum. The brain then integrates this data in a few ways. We get most of our information about a sound from its spectral energy, but a lot of the rhythm and the soundstage comes from recovering precise timing information about transients, like drum hits, by looking across all the frequency bands at once. This perceptual space is very different from analog. And when doing compression, it's always good to be working in a space that's as similar as possible to perception. One key reason is error convolution. See, the binning and the differentiation and the integration that the hearing system does are all kinds of convolution from a math perspective. That means that one part of the input affects every part of the output. In an example we'll return to, deleting even one single sample from the analog representation of a signal results in energy that's spread out across every band of the frequency spectrum. In audio circles, this is called a pop. This convolution makes it hard to figure out what parts of an analog signal are important to hearing and what parts we can throw away. And that's really the game in compression. We get the best results for a given file size if we can figure out how to preserve what's most important. For instance, at the same bitrate, you can have great 4K video or lossless, but 240p video. I'd rather have the 4K. So for efficient audio, we'd like to leave the analog space and get closer to how the brain works. So let's start talking and start listening. Here's a 10-second audio clip we'll use as a reference. For technical reasons, it's not the best reference, but archive.org was under attack when I wrote this talk. So my choices for Creative Commons Music were limited. Please give a few bucks to archive.org.
So let go.
So, I will do something that's common in signal processing, and I will suppress the samples with the lowest energy. This deletes half the information. So modern codecs get a 20-to-1 compression ratio. We're going 2-to-1, so that should be easy, right?
So let go.
Yikes. So if you're a signals engineer, you might have spotted the mistake, which is that it's wrong to think about analog samples having energy on their own. In fact, we added a lot of spectral energy by deleting those samples. And fair enough, but that's also the point. Analog is good for some things, but bad for stuff like this. Now, many of you will hear me talking about frequency and think Fourier transform. So let's explore that. I'm actually going to use a related transform called the DCT. It's the same idea, but tweaked. So instead of giving us back phase information, it folds that data into the same number of magnitude coefficients, and that's just easier to work with. So here's the DCT version. In this case, I'm dropping 3/4 of the frequency, a 4-to-1 ratio.
So let go.
And that's not bad, but you do hear a little weird hissing in the high frequencies, so let's dive into why by doing this again at a 20-to-1 ratio. So in this case, you're hearing how the song kind of stretches out over the whole sample into that shimmering sound. Before zeroing the harmonics, the information from the whole song is all there, but the precise shapes of the song, so to speak, only emerge from the push and pull of all the bands. Delete too many and the features blur out. And it's hard to know which ones to keep in order to get a good result. Again, this is because of error convolution, this time in reverse. With the unwindowed transform, the errors in one frequency affect every time in the song. So we need a hybrid. The brain works with frequency bands, but it also differentiates them through time. So we need to do the same. It turns out we can do this pretty easily. Instead of taking a whole song and transforming it into a spectrum, we can split the song up into short windows and transform each one individually. This is the block DCT. This is a 4-to-1 ratio.
So let go.
And that's not bad, right? But to show you a problem with this, let's go all the way to 100-to-1, and we'll find out why this isn't used directly.
So let go.
Interesting. So in this rendition, it seems like that may not have come through as clearly, but maybe they're doing actually some signal processing in the back to make this sound better. But there is a lot of nasty popping in this version at 100-to-1 ratio. And that, when that happens, it's because we are making things smooth within the block with this DCT transform, but we're not making sure that the blocks join up with each other. And that kind of popping would be really noticeable, although it sounds like this concert hall has some great equipment that's filtering some of that out. So we have one last tweak if you do hear that. We keep the same idea, but we look at overlapping blocks in the screen. And critically, we will then crossfade between those blocks. The crossfade's carefully chosen so that everything adds up to 1 at every moment in time. Let's listen to that.
So let go.
And here, let's take that all the way to 20-to-1.
So let go.
Pretty good for 10 lines of Python. And of course, for a real codec like Opus is going to have a lot more tricks to do way better than this in that same bitrate, but they're based on the same fundamental idea of doing a frequency transform on overlapping chunks. And from here, we can start to explain why gapless is so hard. Because the block nature of these transform codecs mean that they have built-in lag. When you feed in data for a block, you need to join it up with the data from the previous and next block to get the original back out. And that means that you can only get the data from the first part of the current block. Here's what that means for gapless. At the start of a file, you need to put in something to get the decoder started. But if you put an actual signal, it gets windowed by the DCT and some of it gets lost. So actually what you do is you start by feeding in zeros for a little while. And the decoder doesn't really know about this, it's just a simple state machine, but when you decode the media, you actually get back this extra padding information that you put in at the start. The same thing happens at the end, where you have to pad it out to flesh out the final sample. So now we have the first big problem with gapless, which is that you have to delete this padding that was added, which sounds easy, but I wouldn't be giving this talk if it was. So the first problem is, the sub-problem is that you've got to know how much padding was added during encoding. That information gets stored in the container. The good news is the standards for doing this are clear and straightforward, so every encoding application writes this, right? I guess I was too optimistic. Well, let's assume you're using one of the good ones that works. Deleting this padding after you decode it shouldn't be that hard, right? It's just dropping some samples from the timeline. Yeah, okay, I get it. Why would it be hard, though? Money. For a few different reasons. Two of the most prominent are DRM and AC3 pass-through. Many DRM APIs don't let you access decoded media at all, and AC3 pass-through licenses are cheaper than a full-on AC3 encoder license. So some devices won't even include a decoder at all for this audio codec. Both of these mean that platform APIs that you often have access to are passing down undecoded frames rather than raw PCM. And if those APIs don't have an affordance for passing down this buffer trimming info, or if they lose it along the way, you're stuck. A fun problem we've had at YouTube is that as we work with partners on these issues, sometimes they'll add support for gapless, which is great, except if we've been handling some of the stuff at the application level, then the platform starts doing the right thing, we might end up double deleting content and eating into the actual sound parts. So we make sure now that if we do get the chance to trim the media ourselves, we then delete the information in the file before we pass it to the platform so that this doesn't happen. Another issue is that these offsets shift the entire timeline of your media. In Opus, for instance, the timestamps in the file are written inclusive of the padding. The app needs to remove the padding for every timeline operation. It's not hard, but it's just one more surface for bugs. The second big problem has to do with the way these files get encoded. As we mentioned earlier, you have to pad these files because of codec lag. And you can't just pad them with nothing, you actually have to put something into the encoder. And often this is just zeros, but that can be problematic because the hard stop from a periodic signal to the flat zeros has a lot of spectral energy. And even though you throw away the hard stop data on one side and replace it with more of your music, when you compress the frame with the hard stop, some of the spectral energy from the transition will leak backwards into the content portion because of the compression. There are better alternatives. For instance, libopus-enc uses linear predictive coding. This isn't as hard as it sounds. They just slapped some old code from Vorbis in there, but it works really well, terminating the signal quickly and smoothly with low spectral leakage. So it's tier list time. These are sorted in order of the likelihood of getting issues, not necessarily in terms of practicality. The best outcome would be that this is just handled normatively by the codec itself. It's really hard to test this as a complete system. And if the codec could handle its own trimming, encoders could just do what it takes to make this work well, and we wouldn't be having this talk at all. Second best from an artifact standpoint is to only encode whole albums and seek into them when you need to play one track. For YouTube music, this is totally impractical. B tier is all the stuff I described when it works, which of course it doesn't, which is why I'm giving this talk. C tier is a complete absence of gapless awareness. Gapless wouldn't work, but at least the system would be predictable. And I very much regret to inform you that F stands for FFmpeg. Maybe I'm missing something, but FFmpeg's current behavior is insane. You can't even count on it consistently working or not working. I haven't dived deep into the source just yet, but I cannot figure out why FFmpeg has such an unpredictable time accurately playing back the media it created. And this problem is magnified by how important and widely used and beloved FFmpeg is, which is why it's so frustrating that it's so easy to shoot yourself in the foot with it. Even the beautiful LPC trick that Opus does is gone from FFmpeg because of an API difference. So then it really, really makes me sad to inform you that we actually have a special hell tier, and it is reserved for my beloved Opus. This is the same problem. When something is so good and so important, it means the flaws end up being so heartbreaking. In this case, the problem is that Opus basically only works at 48 kilohertz, but all of our studio music comes in at 44.1 kilohertz. We're not going to talk about why. And the signals folks will tell you that digital resampling works perfectly and there's nothing to worry about. And they're right, in theory, that it's just one more step. But what I very much want this community to appreciate is how much shifting a problem like this to someone else can limit the usefulness of the thing that you were trying to build. For instance, a few years ago, we conducted another round of Opus tests that showed it was just still unsuitable for gapless use in music. The artifacts were just too bad. And that's why to this day, we don't use Opus in the YouTube Music app. Spotify doesn't either. And that is, in fact, why I pitched this talk. I wanted to have an explanation for why we couldn't make Opus work with gapless. And then I went to retest, and I couldn't reproduce the issue. Opus works as well as AAC when you use it right. My best guess is that there was a bug in how FFmpeg's resampler interacted with the gapless trimming metadata rather than a bug in the codec itself. But these problems are something that we have as a community an opportunity to confront with at multiple levels. Now, as we as a team, now that we found these, we're going to try to fix them. And we just heard a wonderful talk that explains exactly the process we're going to use to do that. But I'd also pitch that there is an opportunity for this to go both ways at the spec level. That the things that we build are only useful to the extent that they work reliably. And that doesn't just include how we intended them to be used, but how they get used in practice. And so while our tools and specs shouldn't be any more complex than they need to be, I'd like to issue a challenge for us to add a certain level of product focus, even at this low level, of considering how people are using the things that we're building, regardless of how we intended them to be used. And that might make the things that we're trying to build, even more important and even more useful to the community. So, how much do you need to care about all of this? Some. If your service offers music, you should definitely at least get the basics right. But I'd also say that if you're passing your own internal listening tests, you probably don't need to do deep dives into stuff like boundary conditions, especially if our team succeeds at landing some improvements to there so that you can pick those up automatically if you're using standard tools. Modern factors are definitely helping us out here. Some of the most iconic live events are being presented atomically again. And it turns out that music labels are actually adapting. I know I promised, but I do have to mention just one fact about CDDA, which is that for arcane reasons, tracks can only be exact multiples of 588 samples. Well, it turns out today that music labels ignore that old rule for digital distribution and actually do track cuts on 0 crossings, which works better for gapless with 0 passive lossy encoders because there's not as much of a transition. But Dark Side of the Moon still uses quantized track boundaries, so it's possible somebody will still appreciate all of the work we should all do in this space. Anyway, enough about audio. Let's talk quickly about video with audio. Without loss of generality, imagine a service like YouTube Music, where all of your music tracks have a video component for consistency. Let's extend gapless to this scenario. Audio and video have different timescales, so you have to pick one to preserve. Which one is it, and why is it audio? Well, first, let's acknowledge that it is actually hard to handle this on the video side. Just naively clipping the last video frame to the audio duration produces a really short frame, and you might think that's fine because video is just pictures and pictures don't have an intrinsic duration. But if you pass this to a TV, the pipeline says that you're doing a frame rate transition to thousands of FPS, and then it fails. You'll often hear that TV makers say that their pipeline never drops a frame, and that sounds like they're boasting, but it's actually a red flag. What it means is that the system can't handle states like this and will just get confused and fall over. Even pipelines that are quite good can be sensitive to this kind of thing. The cadence algorithms used to match frame rate to vsync windows can get confused when the frame durations get close enough to be able to round over that line back and forth. So it is hard to handle this in the video domain, but audio is even more sensitive. As we've said, the ear can hear even a single sample deletion. So even if you take care to blend the transition, missing audio is much more obvious than a dropped frame. Importantly, the impact of it lingers just beyond just the moment that the frame is dropped. So that's why the audio clock is the reference and video is driven by the audio clock. In this situation, my suggestion would be to avoid feeding the short frame to the decoder at all. That will introduce a small amount of AV drift, which isn't noticeable on its own. It's more like 5 milliseconds for a frame, but it could accumulate over time. So track that error explicitly and incorporate it into subsequent decisions on which frames to keep or drop. But that still leaves us with the same problem as we had with audio on its own. We have to deal with this padding. What happens on a device where post-decode trimming just isn't implemented? Specifically, will we even know that anything went wrong? Well, I prepared a highly simplified diagram to explain this, and I'm not kidding that it's simplified. I gave up adding detail about a quarter of the way through, and there are still a dozen sources of audio clock offset that made it in. This is all highly schematic, but I do want to use this as a thinking tool to understand some of the problems here. If you look at the representation of what an HDMI streaming stick is doing, there are just so many routes to get audio out from the device to the HDMI cable, and many of them depend on the current configuration. So no, there is basically no way that you're going to get feedback from your endpoint that you've accumulated 20 seconds of extra drift. The review website Artings has started to dive into this stuff within their tests of home theater equipment, and the results are exactly what you'd expect. With one exception, for every soundbar they tested, every combination of codec and connection mode resulted in a different sync error, and without any exceptions, all of the eARC delays were big enough to be perceptible. And you can't even solve this by locking to one configuration and setting a static offset. I created a way to remotely measure clock drift, and although the 1080p scenario is only 10 times worse than what you'd consider acceptable on a modern device, the 4K scenario baked the quartz oscillator and the error rate doubled. So there is no solving this problem. But if you, like me, enjoy paying your bills and you're content creators, you might want to know how you make money off of this, which is to say, how do you insert interstitials without making all of these problems worse? The good news is the requirements for interstitials are less severe. We want to stitch media with as little delay as possible, but because things transition back and forth from regions of silence, it gives us much more flexibility over the stitch, which is good because given from the rest of this talk, we have to assume that sample accurate trimming simply isn't going to work on many real systems. So my advice for this situation is to drop any frame that only contains padding, but keep the entirety of any frame that contains content audio. And this is almost as fast as a true gapless transition. It does introduce a little bit of reconstruction error, but it's not sonically available. Opus does a great job of masking it. And it's helped considerably by enforcing that your cut points have silences on either side, which you should do for heterogeneous media anyway. The other thing is that the AV sync error may accumulate. This is quantization error, so in theory it should average to 0, but in practice, it can get excessive if you run into a pattern. So you can do a pseudo-gapless transition to reset that delay when you need to. That's where instead of a gapless transition, you append the media into the future and you issue a seek to clear the pipeline. This can be a great spot to make up a couple frames of latency if you're drifting, which in fact I am with this talk. So I'll end it here and just call it and say thank you so much.